Right. Today we are going to 8%. So graphing was the very first thing we did. So it's been a while since we looked at this. When we graphed our exponential functions, we used an XY chart. So to graph for number 1, we're going to create a chart. I like -1, 0, 1, and 2 because they're easy to plug in. 3 to the -1 is what? 1/3. And -1 power gives us our reciprocal. 3 to the 0 is 1. Anything to the 0 power is 1. 3 to the first is 3. 3 squared is 9. I'm going to plot those points. I don't have room to plot the 9, so I'll just ignore that one. And draw in my curve, which gets arrows at both ends, and remember has a horizontal asymptote there on the bottom, that it should not be crossing into the negative portion of that graph. So then for domain and range. Domain speaks about x's. What x's will this line cover? All of them eventually. On the left-hand side, we can see that's just pointing straight out. It's going to cover that whole number line out to the left. On the right-hand side, it's harder to see because it looks like it's going straight up in the air, but it is ever so slightly budging over also as it goes up. Range talks about y's. What kind of y values will we get? Anything bigger than 0, because that asymptote at the x-axis cuts it off, and we will never get anything on the lower half. So y will only be greater than 0. Question? Here first. What does the +2 do to the graph? Left 2 when it's with the sideways motion, opposite of the direction of the sign. What's the +1 do? So we're going to begin by going to the left and 1 step up. Then we can consider just the base function of 3 to the x, the stuff we have. We already used the 1, so we can just ignore them now and use 3 to the x, which conveniently is what we already did in number 1, so we don't need to recreate our chart. We can just look back to the chart from number 1 and plot those points. But when we plot them, we're going to plot them from the dotted lines, from the place where we shifted to as being the origin. So from where those dotted lines meet, back 1 up 1/3, over 0 up 1, and over 1 up 3. So it has the same shape as the first question since it's the same base function, but it's moved over and up a bit because of those additions. What does that do to domain? It's still all reals. It's still pointing forever to the left, and it's still budging over to the right, even though it's also going up. What about range? Greater than 1, because our asymptote moved up 1 spot with that upshift. So now we're never going to get anything below the line of 1.
Right. The range always be something is greater or less than but not equal to.
Correct. We do not want the so it could be a greater than or it could be a less than if we had the because it'll actually never even touch that line. Number 3, we'll begin by making a chart. (1/2 to the -1 is 2. A -1 power gives us a reciprocal. Anything to the 0 power is 1. So the first is itself, and 1/2 squared is 1/4. 1/2 times 1/2. So we plot these points. Domain. All real numbers. Range. Greater than 0. We didn't have any moving, so that asymptote is still at the 0 line. This is a decay instead of a growth that is going closer. It's becoming more flat instead of becoming more steep, but that doesn't change our ideas of domain and range. Questions? Number 4 uses an E. We're still going to use a chart, but to evaluate these, we'll plug them into the calculator and get a decimal approximation. Now, because that the equation actually already has which is really just e to the first, or e, which is 2.7. Power. When I plug in a 1, which should give me about plugging in 2, I would do e to the negative 2, which is going to be about 0.1. Okay, so we can just plug those in the calculator to get the approximations for them. Just be careful of that negative that's already present in the equation. Then we plot. It looks a lot like the last one. So what about domain? And range? Y is greater than 0. Again, we didn't have any up or down shift, so that asymptote still remains at the x-axis. Questions on graphing exponential functions? Now, some of you may realize, hey, I'm holding a graphing calculator in my hand. I bet it graphs. It does. And that would be an awesome way to check your work. But without seeing the charts and clearly plotted points, I'm not going to give your calculator credit. Okay? You need to earn the credit by showing me that you know how to actually do this. Awesome idea to check your work, though. I would not mind you at all plugging it in and making sure the graph your calculator gives you looks like the graph that you found on your own, but you need to make sure that you're finding them on your own too. Questions? To graph a logarithm, we're going to change it into an exponential. So our first step is going to be to rewrite this as an exponential. What is the base in number 5? 10. Remember, if there's no base written, the little invisible base is 10. So when I rewrite this as an exponential, what will that equation be?
10 over y equals x.
10 over y equals x. There's some enthusiasm there. 10 over y equals x. On the side of the equation that has the numbers. So that's where it's easier to plug something in. So 10 times 1 is the reciprocal of 10, or 1/10. 10 to the 0 is 1. 10 to the first is 10, and 10 squared is 100. And these are going to be some hard points to plot, because this thing is getting insanely large and insanely small very fast. So we'll do what we can with plotting. We're going to go over a 10th, so just a tiny amount, and down 1. Over 1, 0. And 10 would already be way off the graph, but I'm going to plot it anyway to get an idea of the turn that it's taking. So what about domain here? Domain talks about x. It's greater than 0. It's limited by a vertical asymptote. Just as our exponentials had a horizontal asymptote to limit the range, logs, since they are the inverse, have a vertical asymptote that limits the domain. Our x's are cut off, and we're never going to have on the left here. It doesn't look like it's going up very fast, but it is. It's just going to take a whole long time for it to get very high here, but it is. For number 6, we have some shifting to take care of first. What does that plus 2 do? Left 2. Then we can look at the base equation of just y equals the ln of x, ignoring the plus 2 because we already took care of it. We want to rewrite this as an exponential, which would be what? What is the base of ln? E. So e to the y equals x. And as with the last, we're going to choose our y's and plug them in. And we can just plug these in the calculator. Sadly, I already know what they are. Wasted brain space. When we plot them, we're going to plot them from the dotted line. So over 0.4 and down 1, over 1 and 0, over almost 3 and up 1, almost 7.5 and up 2. And that dotted line becomes our asymptote. So what does that mean about domain?
It's greater than -2.
Greater than -2, where that dotted line moved us to. That's where this graph starts. And our range? All rails. Questions were actually special logs. A base of 10 and a base of e are functions your calculator could do. So instead of turning them into exponentials, you could have just put numbers in for x in the original equations and made charts that way. But I am not promising that your test tomorrow will be all base 10s and base e's. So if I give you like a base 4, there's no way to just plug that in the calculator, so you need to know how to rearrange to an exponential. Questions? Simplifying, looking at how the number e works. It works just like any other number because it's just a number. So when we're multiplying. The number 8, we have some coefficients, so I can multiply the 2 times the invisible 1 in front of that other e. And we have some exponents to take care of, and once again we're multiplying, so when we multiply we add. We would have e to the -2. To evaluate a log, remember what a log is asking. It's saying the base to what power gives us this number. So in number 9, what is the base? 10. So number 9 is asking the question of 10 to what power? 1,000. 10 to the third is 1,000. So the answer is 3. When we evaluate a log, it's asking the base to what power gives us this answer. So 10 to what power is 1,000? 10 to the third is 1,000. Now because I went to base 10, we can just put that in the calculator, but number 10 is not a base that we can just plug in the calculator. Questions asked, check. To what power, and I could just start trying things on my calculator. Maybe I'd think it was 4 to the 4th, so I'd plug that in and see if it worked, okay, and adjust from there. Multiplication, they want to multiply every fractions they see. What happens?
Cross them out and get 5.
They cancel, and we get 5. Now, what if they weren't exactly the same? Like, what if on the bottom it was an e to the 3rd? What do we do with exponents when we're dividing? Subtract them, okay? Questions on simplifying? Going to apply 3 different properties, possibly. We won't do all of them on every question, but there are 3 properties that can be applied. The goal of condensing is to take multiple lengths. Second property we're going to apply is what we do when we're adding. When we put additions together into one, what do they become? Multiplications. So we're going to have a log of 8 times x to the 4th. Number 13 uses ln's, but ln's are just logs. They have a special base, but they follow all of the same rules. So the first property we'll take care of is the 3 and the 4, which go up as exponents. When I have a subtraction of logs, what happens when I put them together? It becomes division. First thing divided by second thing. It always comes in that order. Now a point to note. Super common student mistake is to write an ln for both the top and for the bottom. So students will write ln of x cubed divided by ln of 2 to the 4th. Okay? They're all together inside of just one single log. So we don't want a separate log for the top and the bottom. They already were separate when they were being subtracted. When we put them together, they're now just all inside of one.
All right. Could we have written just
That would be fine. Or I'm more concerned with the being applied correctly. That's the opposite process. So everything is already together, and I want to separate it out and give everything its own part. So 4xy, what kind of math is happening there? Multiplication. When I separate multiplication, what will it become? Addition. So we are going to add individually each one of those things having its own log, which happens to be an ln in this question. Number 15, what kind of math is happening inside of the log? Division. How does division separate? Subtraction. So I'm going to subtract the first one minus the second one. It's not totally done yet, though. It's done when there are plain numbers or letters inside. We got to get rid of those exponents by dropping them. So we have 3 logs of y minus 2 logs of x. Questions on condensing or expanding using those properties?
It's 3 log x.
Base formula. Even though our calculator can only do base 10 and base e. The change of base formula is that you are going to take the log of the inside divided by the log of the base. So for this question, that would be the log of 12 divided by the log of 6. do not do any simplification because it actually doesn't work that way. So a lot of times on a problem like this, students would say, oh, I can just save myself some typing and say that's just 2 and do the log of 2. It's not right. Okay, it doesn't work that way to do simplifications. So you need to just type in the whole thing. Being careful to close off the parentheses after you type in the first part. And I get about 1.4. Now I think it's always a good idea to check your answer, so remembering what a log means, this question is asking 6 to what power is 12? So we could check our answer on the calculator by doing 6 to the 1.4, and it should be pretty close to 12. Questions? If these pages were slightly uncomfortable since it's been so long since we've done it, you will notice at the end of your packet there are 2 more pages of practice of these particular skills. I don't have a copy of the answers to pass out to you, but there is a copy of the answers on both RenWeb under the course documents and on the website where I post the videos under the notes portion. So if you wanted to do some extra practice, and then you could look up all those answers online to check and make sure that you're doing them right. Because it's been a long time since we've done this stuff, and so I would really suggest doing some extra practice and making sure that you still have it all after our break. Okay. Equations are what we have done most recently, so hopefully these will be the most comfortable for you in the past couple days. My exponential equations. When the bases are the same, right in the other. So if the bases already match, we just need to make the other stuff match. So we can just match up those exponents. Let's solve this by subtracting 2x from both sides and getting that x is 1. On number 18, the bases are not the same, but could we adjust this so they are the same? How could I rewrite it without changing the values? 3 to the second instead of a 9. So I haven't changed the value because 3 to the second is 9. I've just rewritten it, so now we have matching bases. So if the bases match, then the exponent should match. So x plus 4 should be equal to, what do I do with that stuff? Multiply power to a power, so 2 times x. Same. Could I write them as the same? No. 5 cannot be written as a power of 2. So then we need a new method. How do we undo exponentials? Logs. That's what logs do, is undo these exponentials. So to fix the exponential, we're going to take a log of both sides. It could be any type of log. Log base 10 or log base e would be the most helpful because those we can easily plug in the calculator. But not yet. What do I need to do next? I need to drop the x so that my problem is now a multiplication problem. And how do I undo multiplication? You can plug that in the calculator. Once again, not doing any simplifying, just plugging it in right as is. And we get about 2.3. Once again, checking your answers is often a very good idea. So I could go back to the original problem and say, is 2 to the 2.3 reasonably close to 5? My instinct would say it should be because 2 squared would be 4, so it has to be a little bit bigger than that to make 5.
On the test, are we going to have to, if we round, are we going to have to put the little square thing?
No, you don't need to use the approximation symbol. I would not mark you wrong for writing equals. Not that picky. questions on exponential equations? Log equations then, what we did yesterday. On number 20, what do we notice?
They're the same base.
Everything matches on the two sides so far. Log matches log, 6 matches base 6, so that means other stuff should match. And solve from there. And so through that linear equation, we get an answer of 2. Number 21, we cannot use that process because there's only one log. So the two sides of the equation don't match up right. So how do we undo a log? An exponential. So logs undo exponentials undo logs. So we're going to rewrite this as an exponential. How does that work? What's the base? 5, and that stays the same. And what happens to the other stuff in the problem?
5 to the 30.
It switches sides. So 5 to the third is equal to 3x. The base stays the same. The other stuff switches sides. 5 to the third is 125. Dividing both sides by 3, it does not divide evenly by 3, so I would just leave it. With thirds, I really prefer fractions since it's a repeating decimal. Number 22. Don't have two matching bases, but they're on the same side. So we can't just set their insides equal like we did on number 2. So I want to take those two logs and put them together into just one. They're added, so what does that mean I'm going to do with the insides? Multiply. So these are just like the condensed problems from the previous page. An addition goes together as a multiplication. Then we are ready to rewrite. What is the base?
Y squared plus 6y.
3 to the power of 3 equals the y plus 6 times y. The base stays the same, and the other stuff switches sides. 3 cubed is 27. Students always want to say 9 for this, and they always want to say 6 for 2 to the third. Once we get past the 2 and the 3, it tends to be fine. I don't think I've ever had a student tell me that 4 to the third is 12, but for some reason 2 and 3, we just always jump and just multiply them. I don't know why, so just be careful if there's 2s and 3s that we're actually doing cubing and not just multiplying. Always happens. I don't know why. Y squared plus 6y when we distribute, which makes this into a quadratic equation. So we are going to subtract that 27 over to get everything on one side. You could solve here with your quadratic formula if you like that, or by factoring. I promise to give a factorable problem. And that is my preferred method. So what multiplies to negative 27 that adds to positive 6? Plus 9 and minus 3 will give negative 27 and positive 6. So what are the solutions?
Negative 9 and 3.
Negative 9 and positive 3. But we might have some extraneous answers here. Particularly when you get two answers, you're going to want to go back to the beginning and check them. When we check, all we need to do is make sure that the insides stay positive. If those insides become negative, that's a problem. Just like taking a square root of a negative doesn't work, Taking a log of a negative doesn't work. So negative 9 is going to be a problem for us. And we just want 3 as our solution. Questions on solving log equations? For us, you deposit $1,500 in an account that pays a 7.5% annual interest compounded continuously at the end of 3 years. R is the interest rate, which is 7.5%. How does that go into the equation? 0.075, not a 7.5. I would love to bank with you if that's how you do your calculations. You'll get some ridiculously large answers. Okay, so make sure you turn that percent into a decimal before putting it in your equation. And T stands for time, which in this problem is 3 for 3 years. Plug it in the calculator, making sure that all of that multiplication is happening up in the exponent of E. We get $1,878.48. Questions?